This is lesson 10.3. We're doing compositions and inverses of functions. Really, we're talking about inverses because this is our exponential and log chapter. So you guys just covered a bunch of sections about exponential functions, and then we'll be moving to log functions next. And exponentials and logs are inverses of each other. So we have this lesson kind of right in the middle to learn about what inverses are. So that being said, we're going to quickly review compositions of functions before we get to inverses. So you can see the definition for compositions of functions here. We reviewed this at the beginning of the year. This part here is new notation. You see this on standardized tests or college entrance exams. That open circle there is the same as saying a composition of functions. So we more often see it like the right-hand side, where it said f of g of x. So here's some examples. We're given a couple different functions, f, g, and h, and then we're asked to find different compositions. So in this first example, we're going to start on the inside. We're going to first find what g of 2 is. So if we go to the function named g and substitute 2 for x, we're going to get 2 squared minus 1, or 3. Now, because we're doing f of g of 2, now we do f of that answer, which is 3. So when we do f of 3, we go to the function named f and plug in 3 for our x. So the answer for f of g of 2 is 6. Same idea for the next one. We're going to start on the inside and we're going to evaluate f of negative 4. We go to the function named f and we plug in negative 4 for our x. So that's negative 1. Now using that outer function, we're going to do g of that answer, which is negative 1. Go to the function named g, plug in negative 1, and we get 0. One last time, same idea. So if we go to h of 2, function named h, plug in 2, we get negative 1/3. And that outer function there is f of h of 2, so f of negative 1/3. So we'll do negative 1/3 plus 3, or 8/3. So that slide is mostly review from earlier in the year. This slide, we're doing the same thing, but we're not going to evaluate it in number. What we're going to do is just a composition of functions where we plug one function into the next. So this first example is saying take the function f and plug g of x into it. Well, the function f is x plus 3. But again, it's not saying put x into the function, it's saying put g of x into the function. So what we're going to do is, where there was an x, we are instead going to put what g of x is, which is x squared minus 1. And then you just need to simplify that. So it's x squared plus 2 for our final answer there. Same idea with the second one. We're using the function g, which is x squared minus 1, but instead of plugging in x, we're plugging in the whole f of x into that x. So I'm going to rewrite it and leave a space where x used to be, and instead I'm going to take f of x and plug it in to that space. And then we just need to simplify. So we would get x squared plus 6x plus 9 minus 1, which is x squared plus 6x plus 8. Okay, so moving on to inverses. Just like the word implies here, inverse means we're going to be doing opposites or switching. So in this case, inverse functions switch all of the x and y coordinates. So before we think about that, let's quickly review what it means to be a one-to-one function. A one-to-one function means it passes the horizontal line test. So I could draw a horizontal line anywhere through the function and it would only intersect one time. What that means is that we have a unique x and y, and therefore we could have an inverse which switches all of those coordinates. So let's look at this first example. First it says, use the horizontal line test to determine if it's a function. Well, yeah, it is. Anywhere I would draw a horizontal line here, we would only intersect in one place because it's always increasing. Even this Even that one part that looks like it gets almost flat is still increasing. So we're only hitting in just one place each. So yes, it is 1 to 1, so we can find an inverse. So here's how we graph the inverse. The inverse just switches all the x and y coordinates. So if the original has the point 1, 2, like this point right here, then the inverse has the point 2, 1. I'm going to pick some other points. The original has the point 0, 1, so then we have 1, 0. We have negative 1, 0, so we have 0, negative 1. And those are kind of 3 nice easy points. You could estimate even more, like this one here is at about a half and then a little more than 1. So you could go a little more than 1 and then about a half. Oops, that was ugly, sorry. You could maybe try this point out here. You say, okay, well, it's a little past a half and then almost 1, same thing. So then we'll go almost 1 and say that again, sorry. That point there, let me get a pointer. This one is about a negative a half and almost 1. So then here we'll go almost 1 and about negative a half. So again, we're just kind of estimating here. The point is that we're switching all of those x and y coordinates. So you can see what's kind of happening here. I'm going to do my best to sketch a good picture here. It would look like this. What's really happening is, imagine if we folded that graph along those corners. That's the line y equals x. So picture like this red line here as being like wet paint. And then if we folded it and creased it along this line, it would make an imprint like this. That's the inverse. The inverse is what's reflected around that line, y equals x. Okay, quick example here. The whole left-hand side is a question that was on one of your quizzes earlier in the year. So first we could tell that this relation is a function. You might want to do one of the mapping diagrams like we did last year. 1, 3, 5, and 6, and then 2, 4, negative 4, and negative 12. And you could see that each x value has its own unique y value, so not only is it a function, it is a one-to-one function. The domain is just all of the numbers listed in the x-coordinate position, and the range is the numbers listed in the y-coordinate position. So the inverse then is what we said. We switch all of the x and y coordinates. So here, if we have the point 1, 2, we're going to have the point over here, 2, 1. And I'll just go through the list like that. 3, 4 becomes 4, 3. 5, negative 4 becomes negative 4, 5. And negative 12, 6. So you can see the domain now is 2, 4, negative 4, negative 12. And the range is 1, 3, 5, 6. So what I wanted you to notice here is that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. This makes sense. We said inverses switch x and y. Well, domain refers to the x and range refers to the y. This is just a quick review of determining domain, since that's something you're going to need to do in these next couple examples. Really look down here at this part where it says in other words. In first semester, I may have given you something like this and said, what is the domain? Well, we can't have any values that would make a denominator 0 because that's undefined. So the domain of this first one would be x cannot be negative 3. Then that second bullet point there, I may have said, what is the domain of the function g? Well, we can't have negatives underneath the square root, so the domain would be x plus 1 is greater than or equal to 0, or x is greater than or equal to negative 1. Quick review so we can do the next stuff. Okay, so what we're going to do is find the inverse algebraically and then state the domain and range of each. So let's start with finding the inverse algebraically. The steps are listed here, but I'm also going to just do them out. So the function's over here, f of x equals 3x plus 2. The first step is temporarily rewrite f of x as just y. It'll just make your algebra easier. Step 2 is to use the definition of inverse, which inverse means to reverse your x and y coordinates. So you do exactly like that. What you can see I did in that step was where there used to be a y, I wrote an x, and where there used to be an x, I wrote a y. And now what we do is resolve for the new y. So I'm going to get that y that I just made pink by itself. So to do that, I would do x minus 3 equals 2y, and then divide by 2. So we get x minus 3 over 2 for the inverse. I'm going to rewrite that y as in function notation, which this terminology right here, or this notation here, is, where's my pointer? There we go. This notation here means the inverse. This means f inverse of x in function notation. So let's state the domain and range of the original and the domain and range of the inverse. So I'll do that up here for the original. The domain, x isn't underneath a square root, it's not in the denominator, so there's no restrictions, it's just all real. That's just a diagonal line anyway. And same thing then for the range. And then that makes it nice and easy to find the domain and range of the inverse, because they're going to be the same. Well, the domain is going to be the range of the original, and the range is the domain. But since they were both all reals, they're still both all reals. I just want to look at a graph one more quick time to make sure you guys understand the idea of how an inverse looks graphically. So if we graph that function that we were given in the previous problem, which was f of x equals 3 plus 2x, just using our Algebra 1 skills, that has a y-intercept of 3 and a slope of 2. So I could go up 2 over 1 or down 2 over 1. Alright, it's not going to be perfect on this iPad, but there we go. Now the inverse switches all the coordinates. So if this is the point 1, 2, 3, 4, 5, this is the point 1, 5, then we have the point 5, 1 on the inverse. Right here. Then if it has the point 0, 3, the inverse has the point 3, 0. And then if the original has the point negative 1, 1, then the inverse has the point 1, negative 1. And we could keep going, but I'm going to kind of just try to approximate there. And there it is. Again, we're reflecting this along this diagonal line, the line y equals x. And now you can clearly see that the domain and range of each of them is all real numbers. Okay, same directions. We're going to find the domain and range of both the original and the inverse, and then find the inverse as well. So let's start right away with the domain and range of this one, the original. So the domain here, I see that I have an x in the denominator, so I can't let the denominator be 0. So the one number that would make the denominator 0 is 3/2, so I need to say x can't be 3/2. Now, I don't know the range yet, but what I'm going to do is find the inverse, and then the domain of that will give me that range. So here's the steps again to find the inverse. First, rewrite h of x as just y. Then switch all your x's and y's. So where there was a y, write in x, and vice versa. So now we need to isolate the new y, get that by itself. So there's 2 of them, so we're going to have to get them to one side. It'll take us a few steps of algebra here. So first I would multiply by 2y minus